Welcome to AI Dispatch, your channel for the latest AI videos on YouTube. If you don't want to miss these updates, please like, subscribe, and share. Today's video comes from Y Combinator. Joining us is YC visiting partner Francois Chaubard, who presents a counterintuitive claim. The most transformative AI breakthrough is not a massive neural network, but a 15-line algorithm that borrows from physics. This technique, called diffusion, challenges every conventional belief about data scale, computational complexity, and the fundamental architecture of intelligence. Let's examine his arguments. Suppose someone claimed the most powerful machine learning procedure in history consists of only 15 lines of code. In an industry obsessed with trillion parameter models and data centers the size of small cities, we have been conditioned to believe that more power equals more complexity. Francois Chaubard, a researcher working at the cutting edge of computer vision and AGI, presents a viewpoint that completely inverts this logic. He argues that as AI models have become exponentially more capable, the mathematics behind them has actually become simpler, not harder. This is the flow matching paradox. Francois points out that while traditional machine learning models required increasingly complex architectures like UNets and intricate loss functions, the state-of-the-art approach has collapsed into something elegantly simple. He explains that modern diffusion doesn't need to predict complex data structures, it simply needs to predict velocity. His logic is physically grounded. If you view data generation as moving from noise, which represents chaos, to a clean image, which represents order, the optimal path is just a straight line. By teaching a model to predict the velocity of that straight line, the entire training loop reduces to about 5 to 15 lines of code. This challenges the entire software engineering paradigm that equates lines of code with value. Here, the ultimate sophistication is extreme simplicity. Now, consider how this simplicity shatters our understanding of big data. The common consensus is that to train a high-dimensional model, you need massive datasets, billions of images or petabytes of text. If you don't have big data, you can't play the game. Francois completely rejects this constraint. He states that diffusion models can learn to map between million-dimensional spaces using as few as 30 training images. He uses the example of training a model on just 30 photos of a specific person. Intuitively, this shouldn't work. The mathematical space is too vast and the data points are too few. Francois argues that because diffusion learns the distribution of the data rather than memorizing the data itself, it can bridge these massive dimensional gaps with shockingly little information. This suggests that the data moat many companies think they have might be an illusion. Efficient algorithms can do more with almost nothing than brute force algorithms can do with everything. Yet, while the math is simple and the data requirements can be low, Francois introduces a physical constraint that violates our linear intuition about how time and effort work. In almost every other field of computing, if you want a better result, you just let the computer think longer. If a simulation is rough, you increase the steps. Francois reveals a hard, counterintuitive limit in diffusion models. You cannot simply add more inference steps at test time. If you train a model to denoise an image in 100 steps, and then you try to run it for 200 steps hoping for a super resolution result, the model doesn't just give diminishing returns, it breaks completely. He notes that the output collapses into white noise. This is an inference lock. It defies the engineering logic that says more compute equals better output. In the world of diffusion, the concept of time during generation is structurally bound to the time used during training. You cannot cheat the physics of the model after the fact. This leads us to an even deeper inversion regarding noise and error. Traditional engineering is built on the cleanliness iron law. You want to eliminate noise, reduce error, and keep signals pure. Linear thinking suggests that if you must add noise, you should add it evenly. Francois argues that this linear intuition is exactly what causes models to fail. He explains that adding noise linearly is massively unstable. The reason is that the relative impact of noise changes depending on how much signal is left. Adding a little static to a perfect image is a huge shock. Adding that same static to a snowy screen is meaningless. To make these models work, he describes a beta schedule, a non-linear, carefully calibrated curve, where the error added is constant in impact, not in raw numbers. This is a shift from viewing noise as a nuisance to viewing noise as a precise structural tool that must be sculpted, not just dumped. Finally, we arrive at the ontological shock regarding the nature of intelligence itself. Currently, the world is captivated by large language models like ChatGPT. We assume these are the path to artificial general intelligence. Francois applies what he calls the squint test, and his conclusion is unsettling for the LLM orthodoxy. He argues that if you squint at an LLM, it looks nothing like a biological brain. An LLM generates one token at a time, one word, then the next, linearly, never looking back, never revising. It is a feed-forward process. Biology, however, is recursive. Biology is iterative. Francois believes diffusion is the only architecture that passes the biological squint test. When a human thinks or when a diffusion model generates, it doesn't spit out a final answer incrementally. It starts with a vague concept, which is noise or randomness, and iteratively refines it, sharpening the resolution over time. It captures the entire concept at once and brings it into focus. Furthermore, he points out that biology leverages randomness. Neurons fire stochastically. LLMs try to suppress randomness to stay coherent. Diffusion, however, requires randomness to function. It views randomness as a feature, not a bug. This suggests that our current obsession with LLMs might be a dead end for true AGI, and that the future belongs to models that think by refining chaos rather than predicting the next word. This brings us to his most controversial claim regarding the current state of the AI industry. While the media focuses on chatbots, Francois asserts that diffusion has already eaten almost every other field of AI. He lists the conquests: robotics, weather forecasting, protein folding, video generation. He notes that DeepMind won a Nobel Prize essentially for applying this diffusion procedure to biology. The paradigm shift here is that diffusion is not an image generation technique. That's just a branding error. It is a universal reality engine. Whether it's the trajectory of a robot arm, the folding of a DNA sequence, or the formation of a storm front, these are all just data distributions that can be modeled by reversing noise. He believes the entire economy is about to be redefined, not by text generators, but by these physics-based models that can simulate reality. Francois consistently strips away the computer science abstractions and examines the physics of information. Whether it's the velocity of data, the schedule of noise, or the biological reality of randomness, he views algorithms that mimic nature's fundamental laws as inevitably superior to those attempting brute force solutions. The open question is, if the most powerful AI is actually 15 lines of code that mimics the chaos of the universe, are we prepared for how accessible this power is about to become? If you're interested in the video featured in this episode, click the link below to watch the original.